Welcome to Introduction to Remediation Techniques and Technologies. It takes a team of good people knowing what they are doing to properly remediate a site. You need a qualified staff, including a professional engineer, environmental engineer, or chemical engineering. You need a mobile certificate of approval, a mobile C of A license, which comes from the Ministry of the Environment and Climate Change. A mobile certificate approval allows a company to start remediation within 10 days after submitting its application to the MOECC. If a company does not have a mobile certificate of approval, they must wait 6 months after filing an application before they can begin the process. Soil and groundwater remediation specialists, which include in-situ and ex-situ remediation techniques. We also carry liability and pollution insurance coverage, provide Canada-wide service, and we offer a complete array of chemical oxidants and biological amendments to remediate sites. Most of all, we have a proven track record of successful remediation. Remediation techniques generally fall into 3 categories: ex situ, in situ, and pump and treat. There are advantages and disadvantages to each. In ex situ, which is often referred to as dig and haul, the contaminant is dug out and replaced with clean fill. The contaminated soil is removed to a local landfill. Some of the advantages of this remediation technique is that it's relatively fast compared to other methods. Some of the disadvantages is that it's highly expensive. You're talking the trucking costs plus disposal per metric ton, the hours of disturbance on a property, and putting the property back to its original condition. It is also highly disruptive. Occupants of buildings or commercial operations are disrupted during this process and cannot continue operations or cannot stay in a building. Other disadvantages of ex situ is that it does not solve the problem, but it simply relocates it. We aren't fixing the contaminated soil, but simply moving it from one location to another. And finally, dig and haul does not address the issue of groundwater contamination. It still needs to be dealt with after the soil has been removed. Now, if there's groundwater that has been contaminated, it needs to be remediated as well, which adds an additional cost over and above the soil which has been removed. The process of excavating in order to reach your remedial objectives includes digging down to a floor until you have clean soil. As well, you must dig to the walls to make sure that you have clean walls. Now, one of the issues with this is that when you test the floor and the walls of your excavation pit, you may think that you have everything because where you take a number of different samples from an area, they may or may not have contaminant in them. This isn't to say that areas that you have not tested do not have contamination in them. One of the other issues is that of groundwater, as we mentioned earlier. If there is still contaminant in the groundwater, if the water table rises, then it will smear what contamination is left in the water table throughout your clean zone. So digging and hauling is not a guaranteed method of remediation, although none is guaranteed. These are things to look out for when you're doing a dig and haul scenario only. Another very important consideration when choosing a dig and haul remedial method is infrastructure and the building. When you are digging out underneath a building, there is often the need for underpinning. This could compromise the building, the structure. This is labor intensive and cost intensive, and it drives the cost of remediation up. The other issue that needs to be considered is disruption to the occupants of the building or operations of a property when you are excavating. People cannot stay in a building, a home, any type of residence. Businesses cannot operate while the building is underpinned because it is too dangerous. So when choosing the dig and haul remedial method, one must consider the disruption to the occupants as well. The second option is in situ remediation. This is where we leave the soil in the situation that it is found and remediate it in place using a number of different methods such as in situ chemical reduction, bioremediation, or there are other air sparging techniques and thermal techniques. However, we concentrate on in situ chemical reduction or bioremediation as these tend to suffice most applications for remediation. We treat the contaminated soil and the groundwater using a chemical oxidant or naturally occurring biotics. The advantage of this process is that it is very cost effective, especially relative to the ex situ and the pump and treat systems. It is non-disruptive to operations and or occupants. People are allowed to stay inside the buildings or structures as this process takes place. Businesses that are operating can continue their operations as well and will not lose income during the remediation process. It also solves the problem. It does not simply relocate it. The soil is returned to non-contaminated status after the in situ process. We aren't relocating something, we're actually dealing with the contamination and solving the problem. The disadvantages to in situ or bioremediation is that relative to the site, it may take longer than ex situ. Successful in situ remediation requires that the amendment make contact with the contaminant. This involves a well thought out and properly placed injection strategy. The contaminant only degrades in the soluble stage, which means that if there is soil contamination, the contaminant must desorb from the soil and enter the aqueous phase. Only in the aqueous phase do microbes and chemical oxidants degrade the contaminant. If one does not desorb the contaminant from the soil, we get what's called rebound. That after one has remediated a site or done an injection with a chemical oxidant or a bioamendment, one can test the site and see that it is clean. However, over time, that contamination can desorb from the soil back into the aqueous phase, recontaminating the site. Therefore, when one is considering an in situ chemical oxidant or bioremedial process, one must take into account both the soil and the groundwater contamination. At the same time, one must calculate the contaminant oxidant demand, that is, how much oxidant is needed in order to degrade the estimated amount of contaminant in the soil. There's so much oxidative power in chemical oxidation. We can calculate this very easily. Also, when it comes to specific contaminants, we also understand how much oxidative process that needs, oxidative energy rather, that it needs to degrade into the benign products. Also, one must consider the soil oxidant demand. Oxidants are indiscriminate. They oxidize anything that they will come in contact to, which includes the soil. Therefore, depending on the lithology, each soil type will demand a level of oxidant different from another type of soil. This also must be calculated into our process so that we make sure we get enough oxidant in order to cover the soil oxidant demand as well as the contaminant oxidant demand. The other consideration is porosity. In order to achieve saturation in the contaminated zone, we also must understand the porosity. This is the volume of space between soil particles. We must saturate the zone in order to bring the contaminant into the aqueous phase so that the oxidant or the microbes can degrade it. Part of this is understanding how much pore volume, how much space between the soil particles there is so that we can fill it. These are all part of the considerations when developing an in-situ remediation plan. There are two main techniques when it comes to using bioremediation alone. One can either stimulate the existing microbes in the soil to degrade the contaminants, or one can cultivate a batch of microbes and inoculate the site. One of the advantages of culturing a batch of microbes and inoculating the site is an increase of activity with the contaminant degrading microbes. In order to do this, the cultivating process involves giving them nutrients as they're being cultivated in order to increase the microbe count. One of the other issues that you need to look at when doing bioremediation is a sufficient level of oxygen. This is when you are using aerobic bioremediation. There are two types of microbes. They are aerobic and anaerobic. Aerobic microbes need oxygen in order to metabolize contaminants. Anaerobic do not use oxygen in order to metabolize the contaminant. The majority of microbes with hydrocarbons are aerobic microbes. There are some chlorinated ethylene microbes which are anaerobic, and special conditions need to be created in order to ensure that oxygen does not reach those microbes when remediating such contaminants. However, the majority of microbes are aerobic microbes that digest contamination. In order to use the existing microbes within a site, one must stimulate them by adding nutrients like nitrates and phosphates, and also supplying oxygen to them. Stimulating the microbes is a very delicate procedure in that if you overstimulate them with too much oxygen, which can be used by a chemical oxidant, you can end up killing off microbes rather than just stimulating them. We highly recommend that if one is going to choose bioremediation, that they culture a batch of microbes and then inoculate the site accordingly. Chemical oxidation is a very similar process in that one inoculates the site with a chemical oxidant, which breaks down the contaminant into water, carbon dioxide, oxygen, and carbon. Both bioremedial methods and chemical oxidant methods break down the contaminations into these benign products. There are a wide array of chemical oxidants one can use. There are sodium persulfates, calcium hydroxide, sodium hydroxide, hydrogen peroxide, sodium permanganate, calcium permanganate, potassium permanganate. There is a wide array of oxidants one can use today. The oxidant is chosen according to many different factors, such as lithology, hydrogeology, location, whether or not there is infrastructure, buildings, groundwater levels, types of contaminant, and one can use many different combinations of these oxidants in order to reach their remedial objectives. One of the components when trying to reach a remedial objective is time. Does one want to remediate the site very quickly, or do they have time? Bioremediation does take more time, typically between 1 and 2 years to remediate a site using bioremediation. Chemical oxidation can be used to remediate a site within 6 to 8 weeks. Within 6 months, within 9 to 12 months, depending on the combination and the oxidant used. Certain oxidants react very quickly, such as hydrogen peroxide. Typically, hydrogen peroxide reacts so quickly that a stabilizing agent is added to it in order to give it time to reach the contamination, to saturate the zone before it completely reacts. Other oxidants like sodium hydroxide, they react a little bit slower and makes it a little bit easier to spread them throughout the subsurface. Something like sodium hydroxide activated with sodium persulfate or sodium persulfate activated with sodium hydroxide will react approximately 6 to 8 weeks. So it's a little bit slower than the hydrogen peroxide. The advantage to this is that it gives the amendment time to disperse throughout the subsurface. Another great oxidant combination is sodium hydroxide, sodium persulfate rather, and calcium hydroxide. The sodium persulfate portion of this oxidant will react between 6 to 8 weeks. This is a relatively strong reaction, and although it does not kill off the naturally occurring microbes, it does knock the count down somewhat. So typically, a microbe count in the soil naturally occurring would be 10 to the power of 14, and it might knock it down to 10 to the power of 8, 10 to the power of 7. And so that slows down the naturally occurring biotic degradation of your contaminant. Now, the calcium hydroxide portion of this mix of amendment will continue to oxidize for about 9 to 12 months. This is ideal in that it slowly releases oxygen, helping the aerobic degradation of the contaminant by the microbes. This leads us to another process that we have introduced called bio-augmented chemical oxidation. This is where we will begin a remedial process using a chemical oxidant such as sodium persulfate and calcium hydroxide, and then later on during the calcium hydroxide portion of the inoculation add in some microbes to speed up the process. The advantage of adding the microbes is that they continue to work long after we are gone. Oxidants are spent once they are spent. There's only so much energy within an oxygen or chemical oxidant, and once it is spent, it is done. However, microbes continue to work long after the fact. So it is advantageous to re-inoculate a site and leave some stimulating compounds such as oxygen for the microbes to thrive long after the oxidant has been spent. Other things to consider when choosing an in-situ remediation option is infrastructure. There are some chemical oxidants that will corrode certain metals. There are some oxidants that may damage certain infrastructure, underground infrastructure like telephone lines, certain cast piping, etc. So it is very important to understand the locates, what is happening in the subsurface before one chooses to inoculate a site with the oxidant. So there are many different factors when choosing in situ remediation processes, and it is very important that you are consulting with somebody who is familiar with many different options, not just one. Another consideration when choosing a chemical oxidant is health and safety. Some of these oxidants react very quickly, as mentioned earlier, and it is important that all the proper health and safety procedures are followed in order to ensure that people do not get hurt. On your job sites, there should be yellow caution tape around a site so that people do not wander on and happen to get some oxidant or amendment on them. Fortunately, these chemical oxidants and amendments are flushed off with water, and there is always a safety shower and clean water supply on all of our sites. In case somebody does get oxidant on them, it simply washes off with water. Pump and treat systems involve installing a recovery well into which the groundwater is drawn, then pumped into a mobile treatment unit where it is filtered and the clean effluent is discharged downstream. The advantages of this system is that the setup costs are relatively inexpensive. Although the upfront costs are not very high, the disadvantages to this process is that it takes a very long time to remediate a site, therefore making it quite time prohibitive. It does not address the soil contamination either. It will clean the groundwater, but does not address the contaminated soil. Eventually, over time, as rain and groundwater percolate through the soil, it may draw contaminants into the recovery well to be remediated in the mobile treatment unit. However, as you can imagine, this process takes a very long time. As the time increases, this system becomes very expensive. Pump and treat systems can also be used in conjunction with in situ remedial solutions as well. For example, one would install a recovery well and draw the amendment through the subsurface. This can be referred to as a push or pull pump and treat system. One installs a pump and treat system at downstream of the contaminated area, and then as one injects an amendment upstream, that depressed water table at the bottom of the contaminated zone naturally draws the amendment through the subsurface. This could be advantageous if one is looking to remediate soils underneath large industrial buildings and wants to speed up or increase the flow of the amendment underneath the building. So pump and treat systems are also used to contain hydraulic containment in order to stop contaminant from moving off-site. By depressing the water table in one central area, it creates a funnel effect containing the contaminant. This can be very advantageous during an in situ remediation process as well, as it helps to contain the contaminant as well as keep the oxidant within the contaminant zone. Here's a chart that illustrates well the differences between dig and haul, in situ and ex situ, and a pump and treat system. Here on the left you have the cost, relative cost on the vertical axis, and then you have the time on the horizontal axis. As you can see, dig and haul, in time it's very, very quick, but the cost is very, very high. And on the opposite end of the spectrum, you have pump and treat, which at the beginning, the cost is relatively low, but then gradually increases over time until it becomes very costly. If you look at in situ chemical oxidation, it happens relatively quickly as far as time goes. It's longer than dig and haul, but it is shorter than bioremediation, and the cost is much more cost-effective approach to in situ remediation, or ex situ remediation compared to dig and haul. When you look at bioremediation, these are biotic pathways that do take longer, and you're talking between a year and 2 years, sometimes even up to 3 years, for these biotic processes to complete themselves. Yet the cost again is relatively low compared to dig and haul. Bioremediation can also be a little bit cheaper than in situ chemical oxidation, but again, it really depends on the site. There's a wide range of in situ chemical oxidants and bioremedial amendments that we can use relative to the site. We have a full array of microbes and enzymes from the biotic spectrum, and also these are typically used in wastewater applications as well. So these are common bioremedial products. Same with the chemical oxidation. We have aggressive oxygen release oxidants as well as slow release oxidants. And we can also use these chemical oxidants to speed up the bioremediation process, simply by adding oxygen into the ground to help the microbes do their job. Bio-augmented chemical oxidation is a process in which we combine both bioremediation and chemical oxidation, and there's a lot to be said for this process as it enhances natural pathways to degrade contaminants. Chemical oxidation on its own, it can be very powerful. We can use aggressive oxidants in certain situations where the infrastructure allows us to, and speeding up that process and saving money. Relative to buildings and infrastructure, we use slow release oxidants so that we do not damage such infrastructure and homes, yet still is relatively quickly compared to bioremediation. We also do metal stabilization as well, which is a very different process. And both the bioremediation and the chemical oxidation do remediate the soil and the groundwater. Um, we do use mobile treatment units, but not to actually remediate the site, but rather to achieve hydraulic containment, which is a very different purpose. So they're there for a short period of time relative to using a pump and treat system as the remediation solution. As you can see here on the right-hand side, there is a list of contaminants that we are able to remediate using bioremediation and chemical oxidation. That list is not exhaustive, but it gives you an idea of the extent to which we can treat. I'd like to highlight the second one down, hydrocarbons, which includes gasoline, diesel fuel, gas, home heating fuel, motor oils, etc., and so on. Today, there is such a wide array of chemical oxidants that can be used to remediate hydrocarbons that are tremendously effective. So relative to the lithology, hydrogeology, the situation, the soil textures, etc., we choose different oxidants accordingly. Now, as we had mentioned before, one of the greatest advantages to in-situ remediation is the ability for occupants to stay in the buildings or the homes during the remediation process. And in our next slide, we will show you one of the bio products that we use in order to achieve this. In this video, we will light gasoline on fire and then put it out using BIM 200 cleaner and degreaser. We have mixed down the BIM with water in the hand trigger sprayer. And here we have some gasoline. We have two containers. The one on the right hand side does not have any gasoline in it, and the one on the left does. We've mixed it down about 10 to 1, 9 to 1, so that's approximately 9 to 10 parts water to 1 part BIM. Empty container, you can see there's nothing in there, and then we light this one on fire. It was difficult to see, that's why we did the control, the empty container on the right hand side, and there was about 2 centimeters of gasoline in our container here. It takes about 12-13 squirts to put the fire out. Who knew it was that easy to put fire out using BIM 200? And as you can see, we have some bubbling action there, and the enzymes, the microbes, and the surfactant have killed the fuming, the off-gassing of the gasoline. We will attempt to relight it on fire, and we just let it sit there for a few minutes. And taking an open flame barbecue lighter, we're attempting to relight the gasoline. As you can see, we're holding the flame right down next to the gasoline, and it will not light on fire. As you can see in the video, the gasoline will not relight due to the fact that BIM 200 kills the fumes of gasolines and oil. Considering that we have a product which kills the volatile aromatic compounds, enabling occupants to stay in buildings during the remediation process, and considering the vast array of chemical oxidants and bioamendments at our disposal to remediate sites in situ, we see a lot of advantages to many industries to use in situ remediation. One of those industries would be those who insure buildings for spills of any type, any contamination. And therefore, we have Rick Howard, insurance specialist, here to continue the presentation with his thoughts on in situ remediation and remediation technologies and techniques for insurance considerations.
Bioremediation in a nutshell. When and or where appropriate, conventional remediation techniques such as dig and haul should be used. For example, dig and haul would be used to remove the impact area of a spill in an effort to mitigate the loss by controlling and containing the contaminant. If the contaminant migrates under buildings, excavate the impact area down to a depth that does not compromise buildings or structures. After that, treat the soil and groundwater with bioremediation and or in situ chemical reduction techniques and products. Non-detect. In order to remediate a lost site to non-detect, additional time will be required. Additional product may be required. Additional testing may also be required. Otherwise, you may delay the final testing until it is known that non-detectable levels have been achieved. Bioremediation and in situ chemical reduction keeps working even after the project is complete. With the use of bioremediation and in situ chemical reduction, contaminated properties can be remediated at a fraction of the cost of conventional methods, even if the job is performed at reasonable costs associated with conventional methods. Some of the advantages of bioremediation and in situ chemical reduction are no excavation costs, no trucking costs, no landfill fees, no cost of demolishing a dwelling, no cost of rebuilding a home, no cost of underpinning a home if you do not demolish it, etc., etc. Some losses exceed the property policy limits of a policy. If the loss is confined to the insured's premises, the insured's claim would be restricted to the property policy limits. I can't see how someone could remediate a property within the policy limits of coverage if the scope of repair includes the demolition of a dwelling, excavation of the contaminated soil, trucking of the contaminated soil to a local landfill, payment of the landfill fees, replacement of the contaminated soil, replacement of the dwelling, etc., etc., etc. Property/liability policy limits can also be affected. If the contaminant migrates off-premise, in other words, if it gets down into the groundwater or migrates onto a neighbor's property, this would trigger the liability limits of your policy. Again, I have trouble understanding how a property can be remediated within the dwelling and liability policy limits if the scope of repair includes the demolition of the insured's dwelling, excavation of the contaminated soil, replacement of the contaminated soil, remediation of the groundwater, landfill fees, etc., etc., etc. Untenable dwellings. When properties become contaminated, we can remediate the property without making the dwelling untenable. If a dwelling is excavated to the point that it requires underpinning or demolition, obviously there would be an exposure to an additional living expense as the insured's dwelling would become untenable. Very little, if any, exposure to claims for additional living expenses when making use of bioremediation and/or in situ chemical reduction. If the insured is not required to uproot their family and locate alternative living quarters, they are less inconvenienced by the loss. As we all know, these claims become costly and can add frustration to the claims process, as all insureds can experience difficulties in understanding the limitations to these claims. If an insured becomes exposed to a subrogation claim, you may wish to retain the services of Golden to provide you with our opinion as to what the scope of repair should have been and at what cost we could have remediated the property. This information will allow you to defend the damage aspect of the claim. Also, during our investigation, we may identify mistakes that may have been made by the remediation firm that performed the actual remediation. Also, we can provide you with some insight as to the actual remediation costs that were incurred by the plaintiff. We may be able to identify costs that are unreasonable, such as landfill fees, excavation costs, trucking costs, etc. Golden understands the claims process. Golden understands your needs as well as the needs of your policyholders. Golden understands the concept of estoppel. Golden understands the need to document the origin and cause of a loss and to preserve all of the evidence. Golden understands the need to properly control and contain the contamination to mitigate the loss. Golden understands the information you need to gather. Golden understands the need to promptly communicate our findings, as you need to make informed decisions in a timely manner. Golden will comply with all of your reporting requirements. With Golden, you and your policyholder will avoid policy limit issues. When remediating fuel oil spills with bioremediation and/or in situ chemical reduction, everyone wins. The reinsurer wins, as they're able to reduce their reserves. They reduce the number of claims that exceed the insurer's retention. They reduce their exposure to claims that actually exceed the insurer's property loss retention, and they reduce their exposure to claims that exceed the insurer's liability loss retention. The insurer wins, as they are able to reduce their exposure to remediation costs on all of their losses. They're able to reduce the number of losses that exceed their retention. They are able to reduce their loss ratio with their reinsurer. They're able to reduce their reinsurance premiums with improvement in their loss ratio. They actually eliminate their exposure to additional living expense claims, and they're able to easily justify remediation costs for subrogation purposes. The insured wins, as our services eliminate the need for them to uproot their family and relocate to temporary living quarters for an extended period of time. During the remediation process, the insured is able to maintain their normal standard of living throughout the remediation process. We also eliminate the exposure to claims costs that may exceed their property policy limits and/or their liability policy limits. The insured wins, as our services eliminate the need for them to uproot their family and relocate to temporary living quarters for an extended period of time. During the remediation process, the insured is able to maintain their normal standard of living throughout the remediation process. We also eliminate the exposure to claims costs that may exceed their property policy limits and/or their liability policy limits.
Now that we have considered remediation technologies and techniques and looked at the advantages, disadvantages to each, especially many of the advantages of in-situ remediation, we're now going to give a short overview of the process in which one might find themselves who has encountered contaminated soil and groundwater on a site. First of all, contamination is discovered. The step one is to delineate the scope of the contamination. So this is done by determining the width of the impact, the depth of the impact. Basically, we find where the oil has gone. And once this is done, then we go to step two, and based on the information that we get from the delineation, we develop a remediation plan. Included in that remediation plan will tell us the lithology, the type of soils that we're looking at, the hydrogeology, what we're looking at as far as groundwater flow, groundwater levels, etc. And then we determine what kind of injection processes are going to be needed, as well as in situ chemical reduction or bioremediation, or a combination of both. After this is determined, we do the implementation. We take our remediation plan and then we implement it. Do you remember, during this process, occupants are able to stay inside their home during the entire remediation process. They do not need to relocate. We don't dig out underneath buildings or underpin because there is no need to. The only ex situ process that is involved is digging out the immediate impact zone. For example, where a home heating fuel oil tank has discharged its oil, we will dig out that immediate impact area, but there's no need to underpin buildings. After the plan is implemented, the results are verified by a third party, like an environmental engineering firm comes in to verify the results, and then we have achieved our remedial objectives. So this gives a brief overview of the system in place in order to successfully remediate a site. Now let's take a closer look at some of these steps. So step one, delineation. This is very, very important because without the site characterization, one can go very wrong with their remediation plan. The first part is to establish containment if necessary. Our priority is to stop the contaminant from spreading further than it already has. Then we move on to delineate the scope of the contaminant. We need to determine, first of all, the contaminants of concern. What are we dealing with? Second of all, we need to deal with the source of the contaminant, often very tied into the determining the contaminants of concern. Identifying a holding tank, an oil tank, storage drums, uh, processes, manufacturing processes which may leak contaminant. These are all the considerations when determining the contaminants of concern and identifying the source. There's no point in remediating a site if you still have contaminant coming from the source. Next, we identify the plume. We need to know the width of it, the vertical impact, the depth. We need to know whether or not the groundwater has been impacted. Also, we need to identify the lithology and the hydrogeology. What are the soil types we are dealing with? This is very important because if we are doing an in-situ remediation plan, we need to determine the soil oxidant demand as well as the contaminant oxidant demand. We determine the contaminant oxidant demand by knowing what the contaminant is and approximately the volume of contaminant in the soil and the groundwater. How much has actually leaked? Then we have to look at the lithology to understand what soil oxidant demand will take up our amendment, energy from our amendment. This needs to be combined with our chemical oxidant demand. This is a very important step, and we must identify what type of soil we are dealing with in order to inject the proper amount, enough chemical oxidant. We also need to look at the hydrogeology. Is the groundwater table moving quickly or slowly? What about the capillary fringe zone? That is the zone where the water table is low in the summertime and rises in the spring. That zone in there is called the capillary fringe zone. We need to understand over a year exactly how the groundwater table is fluctuating. We also need to understand the direction of the groundwater flow. This will determine injection strategies and will help us to understand exactly where the plume is. Then we need to move to the site characteristics such as above ground structures. Are we dealing with buildings? Do we need to get underneath the buildings? Can we get inside the buildings? What is the access like? Do we have underground structures, infrastructure such as sewage and water, communication cables, etc. What is our access? We need to do proper locates in order to establish safe injection points. What about surrounding properties? Do we have access surrounding properties? What kind of activity goes on the site as well? This can determine which oxidant we choose. Then we decide what our remedial objectives are. This involves the Ministry of the Environment and Climate Change as they set site standard requirements. Things to be considered are nearby streams, lakes, marshes. Is it potable water, non-potable water? Is it a residential site, commercial, industrial site? These are sensitive issues that need to be considered when determining what is required, the remediation requirements are from the Ministry of the Environment. And then we need to also consider our time objectives. Does the client need this done quickly, or do they have time? And this will determine which oxidants or process we choose. It is imperative that the delineation is done properly. One cannot prepare a remediation plan and expect it to work successfully if we do not understand the subsurface, where the contaminant is, and what type of subsurface we are dealing with. So one takes the information from the delineation and develops a remediation plan. So first of all, we determine what area is required for the remediation. We determine the volume, the cubic meters of contaminated soil that must be remediated. So then we approach it with, are we going to do this in situ or ex situ? Are we going to use a combination? Easy access areas or immediate impact zones? Will we dig those out or will we leave them? Will we simply do in situ remediation? Then we look at our amendment options: chemical oxidation, bioremediation, bio-augmented chemical oxidation, and all these are determined by the previous factors set out in the delineation. We look at our injection options. What type of soil do we have here? Is the porosity very tight? Do we have lots of volume we need to put in? Is hydraulic conductivity high or low? We also look at an injection schedule. Certain ground types take amendments in certain volumes over time. So we look at injecting over time. How quickly can we inject? How quickly can we achieve saturation? We look at containment procedures. How do we contain the contaminant as well as the oxidant going into the soil during the injection process? We then look at health and safety procedures. Okay, what do we need on site? How do we keep people safe? What are the MSDS sheets, the safety requirements of each amendment? Then we look at time, how much time this will take, how much time it will take to install the injection options, how long to put the amendment into the ground, how long is it going to take for the oxidant to cure or the amendment to cure. All of these factor into the costs, which are estimated in this remediation plan. Then all this information is reviewed with the property owner, an environmental engineer, necessary contractors, and necessary stakeholders. When it comes to the implementation of the remediation plan, everybody's responsibilities are clearly defined. For example, an environmental engineering consultant, they perform the delineation. They provide all of the information that the remediation contractor will use to develop a remediation plan. We also need drillers, properly licensed drillers, in order to install the injection points, to install recovery wells, to do the drilling for the soil and installing monitoring wells. These are separate contractors. Also, we may need excavators, an excavation contractor, again with the licensed equipment to come in and properly excavate the immediate impact zone or to install a recovery trench, etc. Then we have the remediation specialist and tech provider. The remediation contractor provides the oxidants and the injection equipment itself and the remediation plan, and all of this is done in consulting with the environmental consultant and the property owner. Then finally, we have the remediation plan to be executed. We secure the necessary amendments, the necessary scheduling for the drilling, installation of the wells, and then we submit our mobile C of A to the Ministry of Environment and Climate Change. After all this is done, the environmental consultant will come back after the remediation plan has been completed and test the soil. is very important to note that the company that does the delineation is not the company that does the remediation process. The company that does the remediation process does not confirm the results. All of this is done at arm's length in order to assure the data is reliable and your remediation plan is achieved. We will now take a look at 4 case studies as they involve insurance claims on homes. Our first job is called Pigeon. The situation, we have a residential fuel oil spill. There was approximately 600 liters of heating fuel spilled that discharged from the tank. The contamination was visible on the inside of the basement wall. It moved under the basement floor to the drain, followed the drain to a nearby ditch which flowed into a pond located on the property. So the task was number 1, emergency containment. Make sure that the oil was not spreading further. Second of all, to remediate the soil and the groundwater, the foundation of the building, and the concrete floor. There was a dig and dump proposal. This involved underpinning the home, excavating the contaminated soil, replacing it with clean fill, rebuild the foundation, and re-pour the concrete floor. The estimated cost for this project was $250,000. This did not include the groundwater remediation. In this particular project, the groundwater table was relatively high, and in the spring would push up against the bottom, the underside of the concrete floor. In this project, there was a significant amount of impacted groundwater. We proposed doing an in-situ bio-augmented chemical oxidation method, which involved remediating the soil and the groundwater in situ, where it was. First of all, we would excavate the immediate impact area. This is where the oil tank was sitting, and there was heavily oil-saturated soil directly underneath it. We would only excavate that immediate impact area, not underneath the building, just down alongside the building. Then we installed containment booms and a containment ditch along the pond down to the pond and in the pond. Then we flushed the foundation wall and under the concrete floor with the BIM 200, which you saw demonstrated in the video earlier. This killed all the volatile aromatic compounds so that the family could stay in the home. Then we injected a mix of sodium persulfate and calcium hydroxide, which is an oxidative amendment. This is the in situ chemical reduction portion of the project. Then we applied a hydrocarbon digesting microbes to the soil and the foundation after the sodium persulfate and calcium hydroxide had done its job. The results was successful remediation in 12 months, and the actual invoice was $75,000. This is the entrance to the home, and as you can see in the very center of the picture, the bottom left-hand side of the house, there are some pale green tubes sitting right in front of a tote. This is the former location of the oil tank. Both of those totes were used to mix the sodium persulfate and the calcium hydroxide solutions. This is a photo looking from the back of the house, the pond area, up to the house. The top left of the screen is a photo of the pond where we have some booms and pads to capture any excess oil or any oil that had flowed into the pond. We didn't see any oil visually, but this was taken just as a precaution. The bottom left photo, you can see there is a ditch of rock in the bottom right-hand side of the photo, and along that ditch we have put some retaining ponds and some booms and pads as well to capture any oil that may seep down towards the pond. And the photo on the right, you can see the drainage tube. That tube leads all the way up to underneath the floor of the basement of the house. This is the photo inside the basement of the home. As you can see, there is a block wall made of native stone from the area. It would have been a lot of work to have underpinned this home, dig all of that out, dispose of that rock, as well as the concrete floor. Above the radiator, the picture on the right, that's where the oil tank had sat, and so it's just outside of this wall. When we excavated the impact area on the opposite side of this wall, took that soil out, we also sprayed down the stone on both sides with the BIM 200 in order to kill the odors. There's another advantage to adding the BIM. It also helps break up the oil and make it more available to hydrocarbon digesting microbes and the chemical oxidant. The BIM does contain hydrocarbon digesting microbes as well as enzymes that break down hydrocarbons, which helps to accelerate the process with the chemical oxidant. On the picture on the left-hand side, you can see two drains there with the J-plugs, yellow J-plugs in them. These were used to inject the amendment into afterwards, and as we were injecting the amendment from the outside, you could actually see it flowing out from underneath the foundation rock there, and as we traced the amendment flow underneath the concrete floor through those injection points, we could see the amendment flowing nicely underneath the floor. We had great hydraulic conductivity there, which means that the amendment moves nicely through the subsurface soils. Here we have a picture of the circulation pump, which is mixing the sodium persulfate and the calcium hydroxide. This is a relatively simple procedure, as you can see, and the family can come and go. They can live in the home, they can go about their daily business as we continue this process. The sodium persulfate reacts relatively quickly, between 6 and 8 weeks, compared to hydrogen peroxide, which reacts 8 to 12 days, up to 2 weeks. This is slow. So it's a soft reaction, but it is still relatively quick when it comes to microbes. We mix this with the calcium hydroxide, which extends the oxidative process between 9 and 12 months. It is during this process that we inject the microbes so that they're not killed off by the sodium persulfate. As you can see in the background of the photo on the left, there is a tote sitting there beside the building. That tote is full of water. It is there just for health and safety reasons, just in case somebody gets some of the product on their skin. You simply rinse it off with water. It does not burn immediately or react immediately on your skin, so you have time to go over and rinse it off. This is a relatively safe amendment. All of the amendments or oxidants and bioamendments come with the material safety data sheets or safety data sheets, which are well reviewed, and the proper protective equipment and procedures are always used on each site. In summary, the dig and dump proposal was an estimated cost of $250,000. The groundwater remediation was not included, so it would be added over and above the $250,000, which typically includes a mobile treatment unit, which are very expensive in the long run. They would have to relocate the residents during the remediation process. Remember, this is a family of 4. They have work, they have school, etc. So this is a very disruptive process. And there was high potential of damaging this home during the underpinning. This was an older home, as you can see by the foundation, with a number of renovations done to the home. It's been very well kept, which makes it very difficult to underpin. The in-situ bio-augmented chemical oxidation process, actual cost on our part was $75,000. That does not include the environmental engineering's cost of delineation and verification of results. The groundwater remediation is included in that $75,000. As I had mentioned earlier, in-situ chemical oxidation and bioremediation does remediate groundwater as well as the soil, and the residents remained in home during the remediation process. This particular project was done out in the east coast of Canada, and we source local contractors to do the digging, the excavating, etc., to keep costs down. This is a very efficient way to remediate sites all across Canada. Our next featured project is in Brockville, Ontario. Brockville is significant in that the entire area is on bedrock, a limestone bedrock. There is very little overburden. Many people believe that bedrock cannot be remediated. However, this is not true. The situation of approximately 600 liters of heating fuel discharged from the holding tank inside the garage adjacent to the home. The oil had migrated into the bedrock and made its way into the well. Oil was seen coming from the taps of the home. There was a 3-car garage, an all-brick raised bungalow of approximately 4,000 square feet, built directly on top of this limestone bedrock. So the task was emergency containment and remediate the bedrock and the groundwater. There was a dig and dump proposal to demolish the home, to excavate by blasting the contaminated bedrock, replace with clean fill, rebuild the home. The estimated cost for this remediation option was $3,500,000. We proposed an in-situ chemical oxidation process. First of all, our job was to establish a clean water supply for the residents and to flush the plumbing system. We used the existing water well as a recovery well and installed a mobile treatment unit only to establish hydraulic containment. Using their existing well, we were able to depress the water table in the exact area needed for this process. So we were not using the mobile treatment unit to remediate the site, but rather to establish hydraulic containment so that the contamination didn't move further off-site. We used chemical oxidation. In this case, we used stabilized hydrogen peroxide. And the reason that we used hydrogen peroxide on this particular job is because of its quick reaction. Moving through bedrock, you want your oxidant to react quickly when it comes in contact with the contaminant. If you use an oxidant similar to the one we used on the pigeon job, it would take too long to react with the contaminant. Hydraulic conductivity through this particular bedrock was very fast, so we needed a quick reacting amendment. We also used the BIM 200 to remediate the impacted concrete floor inside the garage down at the bottom of the stairwell where the oil tank was sitting. This also enabled the residents to stay in the home during the remediation process. Then we installed screen wells along the perimeter of the impacted zone. We installed injection points at the source of the impact and then installed an injection system connecting all of the wells together. We used the existing water well as our recovery well and injected the stabilized hydrogen peroxide into the screened wells, which was drawn towards the recovery well. Upon successful remediation, we decommissioned the former water well and installed a new well upstream as the new water supply to the home. The result was successful remediation in 4 months. We saved the home. The homeowners continued to live in the house during the remediation, and they were thrilled. This was actually their dream home that they had built together in the Brockville area, and were very upset at the idea of having it demolished and having to rebuild it again. The actual amount invoiced was $300,000. Here in the bottom right-hand side of the screen, you can see the limestone of this area. Directly above it, all of that grass around the home is added overburden. It was added on top of that limestone. The home, the foundation of the home and the concrete floor sit directly on top of that limestone that you see in the bottom right-hand side of the photo. Above that, where you see the top right, where you see that sea container, that is our mobile treatment unit with the activated carbon and necessary filters. It was discharged towards the left of that to the back. You can see where there's a tree house. That is where the clean effluent was discharged. To the right of that sea container, you see a recovery tank that we used. We pumped from their existing well into that tank, and that was our oil water separator. It was a very large oil water separator, but considering the volume of oil that we were pulling out of the well, it was necessary and very efficient. The top left, you can see this is a photo of the well casing. Top left photo, you have 3 there in succession. The one on the left, top left, there's an injection head into the ground, one of the surrounding injection points with the screened wells. In the middle, that is their water well casing. This is near the beginning when we started the injections, you can see how brown the foaming and oxidative reaction is when we hit it with the hydrogen peroxide. And on the right, near the end of the project, you can see how clean that is. Then below that, this is the stairwell, the bottom picture, the three photos at the bottom of the picture on the left-hand side. That is the oil tank at the bottom of the stairwell. To the left of that stairwell is their three-car garage, and to the right is the home. At the bottom of the stairs is a doorway that goes into the home. The middle photo, you can see the oil-soaked concrete and the foundation wall. This was all cleaned and remediated using the BIM 200. There was absolutely no stain and no odor. BIM will eat hydrocarbons in concrete, rock, stone, porous materials, as it consists enzymes and microbes that eat, metabolize, degrade hydrocarbons. There you can see a little bit of the oil had seeped up on the frame of the door going inside the building. It was all remediated, and it also kills the aromatic compounds as well, so the family was able to stay in the home during the remediation process. This drawing illustrates the situation and the system we set up to remediate the groundwater and the bedrock. As you can see, the reddish plume area is where the oil had leaked from the tank. The tank sat right between the garage and the home, and the water well was downstream from where that tank had leaked. We used the water well as our recovery well, which depressed the water table and drew the oil into that water well. Then it was pumped from the well into the oil water separator and then into the mobile treatment unit, and the effluent, clean effluent, was discharged behind the property. This system was set up in order to establish hydraulic containment so that the contamination would not spread further as we implemented our remediation plan. Our next case study is situated in Northern Ontario, just outside of Huntsville, called White Pine Road. The situation, we have a residential fuel oil spill. Approximately 900 liters of fuel was spilled. Contamination was visible on the basement wall. This was a well-treed property which had a steep slope to the lakefront. The task was emergency containment. First of all, to ensure that that oil did not reach the lake. Second of all, to remediate the soil and the impacted groundwater. The dig and dump remediation proposal included demolishing the home, excavating the contaminated soil, replacing with clean fill, rebuilding the home. The estimated cost is $2,500,000. Unfortunately, because of the nature of the property, the building could not be underpinned but would have to be demolished in this particular situation. The in-situ bioremediation proposal for this site was to remediate the soil and the groundwater in situ, to excavate the immediate impact area, to install containment booms along the lakefront, apply hydrocarbon digesting microbes to the soil and the foundation, and install a mobile treatment unit for groundwater remediation. Also, the purpose of the mobile treatment unit was to establish hydraulic containment and to stop the groundwater flow from reaching the lakefront. So the purpose of the mobile treatment unit was twofold. The results was successful remediation in 14 months, and the amount invoiced was just over $500,000. This is a bioremediation and mobile treatment remediation plan combination of the two. We used the BIM 200, which contains the hydrocarbon digesting enzymes and microbes, to flush the site. We circulated the BIM 200 through the soil and down into the recovery well and back up into the mobile treatment unit. This is the idea of a push and pull system with a mobile treatment unit and an amendment. And the reason for using the BIM in such a manner is the plant-based surfactant in the BIM, which would pull the hydrocarbons, the oil, out of the soil and draw it into the recovery well so that it could be treated in the mobile treatment unit. After a series of flushing, we did an inoculation of microbes, hydrocarbon digesting microbes, to let them sit on the site over the winter time. This is a view from the lake, actually standing on the dock up to the home. As you can see, there are numbers of pebbles, cobblestones, small boulders in the soil. We had excellent hydraulic conductivity, which made our system work very efficiently. Also note the trees. It's a very well mature treed area, and combined with the steep slope, to tear down the home and excavate all that soil would have been very costly. This view is along the side of the house looking upwards. This gives you an idea of how steep the landscape was from the home down to the waterfront. At the very top, where one of our personnel is standing, to their right, our left, was where the 900-liter oil tank sat. This is inside the basement, looking towards the back of the house. As you can see, the wet patch on the concrete block is oil. We treated that with the BIM 200. BIM 200 in clinical tests has shown to eat hydrocarbons out of 2 feet of solid concrete. So this proves very well when flushing and cleaning concrete block. We did not remove that concrete block. It stayed in place as we remediated it. Also note that on the outside of this wall where the tank sat, we did dig out the immediate impact area where the 900-liter oil tank sat. We dig down to get the oil saturated soil out of there to stop further migration, but we do not dig down so far as to compromise the building. You can also see along the very bottom of the concrete block how the oil has seeped through there as well. Sometimes it is advantageous to break up the concrete floor in a given area. Not always, but in this case, it did prove to be advantageous in that it gave us direct access to oil-soaked soil underneath the concrete floor. If we were using a chemical oxidant, we could simply drill holes through the concrete floor and inject enough volume that it would push up against the underside of the concrete floor. However, as we were using microbes and going through the winter time, opening up the concrete floor allowed for great access to do injections as well as to aerate the soil. Remember, with bioremediation, the majority of bioremedial microbes are aerobic and therefore need oxygen. This is a photo of our recovery well. As you can see in the photo on the right, there is a sheen of oil sitting on the groundwater. The photo on the left shows how close we actually are to the lakefront. There's the well pump being installed, and this will trap the oil from migrating further towards the lake. Any oil that has moved towards the lake will be pulled back into this funnel as we depress the water table. These containment booms were installed just as a precautionary measure. The oil had not reached the lakefront. As you can see in the distance in the photograph, That area in the background is a waterfowl sanctuary. Because of this extra sensitive area, there were a number of different regulators on site monitoring this project, including the Ministry of the Environment. They were very pleased with how this project went. They saw the hydraulic containment had been established. They also liked the use of naturally occurring microbes in a bioremedial approach because of this nature sensitive area. Another photo looking along the side of the home and the property gives you another idea of how steep the landscape was down to the lake. Again, the property owner was very happy that we saved all of his trees, that the Ministry of the Environment was very happy that the mature trees were not taken down either. And the homeowner was very happy because what we do not see is that inside this home is a lot of woodworking built right into the home itself, which all would have been lost if the home had been demolished as required with the dig and dump scenario. So a quick recap of this project at White Pine Road. The dig and dump estimate was approximately $2,500,000, which did not include the water remediation. It would have destroyed the mature well-treed area and disturbed the lakefront. Our in-situ bioremediation proposal cost just over $500,000. The groundwater remediation cost was about $100,000, but keep in mind we were using the mobile treatment unit in order to establish hydraulic containment. So we basically used it for two purposes, one for remediating the groundwater as well as establishing hydraulic containment. These are efficient ways to use pump and treat systems. The in-situ bioremediation method also saved the trees and the home. Our next featured project was in Mount Pearl, Newfoundland. Situation was a 600-liter heating fuel tank discharged adjacent to the home. The oil had migrated along the foundation wall, under the footing, and followed the weeping tile halfway around the house. So our task was emergency containment, then to remediate the soil, the foundation, the footing, and impacted weeping tile. There was a dig and dump proposal to remediate this site, which involved underpinning the home, removing the neighbor's paved driveway, and shore up the neighbor's home, to replace all of this with clean fill, then replace the neighbor's driveway, rebuild the foundation of the house, and re-pour the concrete floor, refinish the basement, all at an estimated cost of $500,000. We proposed an in-situ bio-augmented chemical oxidation method to remediate this site, which involved removing the immediate impact area where the 600-liter tank sat. Again, we just excavate that immediate impact area without compromising the building. Then we used BIM 200 to flush the foundation, the footing, and the weeping tile. Keep in mind that BIM 200 contains enzymes and microbes that digest hydrocarbons. As those microbes are left behind, they will continue to eat any contaminant left behind. Then we installed injection wells along the foundation of the wall down to the footing and throughout the impact zone. This was very efficient in that as the immediate impact zone was excavated, at the same time we installed injection wells. Then we removed a section of the concrete floor on the inside of the impact area for easy access. Very similar to White Pine Road, removing a section of the concrete floor on the inside allows for very efficient access and is very easy to replace. Then we injected stabilized hydrogen peroxide as our oxidative amendment. We injected hydrocarbon digesting microbes after the major event of hydrogen peroxide into the soil. And the reason that we do this bio-augmented approach is to re-establish the microbe hydrocarbon digesting microbe count into the soil so that if perchance there is any residual, they will continue to do the work. The results was successful remediation in 10 months. The homeowners continued to live in the house during the remediation process, and the actual amount invoiced was $80,000. One of the reasons that stabilized hydrogen peroxide was used was the high hydraulic conductivity in this soil. The overburden consisted of large pieces of gravel, some large stones, very loose soils, and it was sitting on top of the bedrock. The oil in this particular situation had gone straight down, and there was very little lateral disbursement. Therefore, with such types of hydraulic conductivity, we need an oxidant that is going to react very quickly as it is moving through the subsurface. The photo on the left-hand side is from the back of the house. The driveway on the right-hand side of the house would have to have been taken up if the home was to be underpinned and dig and haul be chosen as the remedial effort. We saved that driveway and any potential damage to that neighbor's home. You also see a tank that is used for mixing. We bring in the amendment in concentrated levels and then mix it as we do the injections. On the right-hand side is a picture of the left-hand side of the home. This is where the tank had been sitting. The tarps are there in order to slow down erosion from the rain. You can see the safety fence along top. This is a neighborhood, and the excavation pit is completely fenced off so that children and unauthorized personnel cannot get into this area. On the left-hand side, you can see the bottom portion of the other neighbor's home. There is a paved driveway there that would have had to have been taken out, and the side of that building would have to have been shorn up if the impacted building was going to be excavated as a remediation effort. This photo shows the inside of the wall adjacent to where the oil tank had been sitting. Again, the concrete floor was dug up for easy access. We did also inject the microbe component, so this was advantageous. You can also see in the bottom left-hand side the BIM 200 surfactant that we were using to flush the foundation wall with, the outside concrete brick, and the weeping tile. So there's great access there. We had a great saturation with the BIM 200. On the top right-hand side, it is difficult to see, but there was an accent point to the weeping tile there, which was dug out. You can see in the picture below it a little bit better as it's dried out a little bit, where we accessed the weeping tile and flushed it clean. Looking at the photo at the top left-hand side, we have installed injection tubes. As we were backfilling, that saves a lot of time and effort to install your tubes at the same time as backfilling. Because of the excessively high hydraulic conductivity in this lithological type, we did not need to install injection heads. It did not need to be pressurized. Everything was injected gravity feed. The bottom left-hand side, you can see some of the totes there and mixing containers where we prepared the amendment. Again, everything is fenced off for safety. The middle photo shows the trench at the back, where we also injected amendment to let it seep down and reach that weeping tile at the back of the house. Again, as you can see, the top right-hand side, everything is fenced in accordingly for safety regulations. And you've already seen the photo at the bottom right-hand side of the picture. Our final case study is found in Sault Ste. Marie. The situation is a residential fuel oil spill. Approximately 600 liters of heating fuel had spilled, discharged from the tank. The oil had migrated under the home into an abandoned O-pipe down to the beach and approximately 150 feet into the lake under the ice. The task was to remediate the soil and the groundwater, and to remediate the lake water, the ice, and the snow. This was an in-situ bioremediation plan, which involved excavating the immediate impact area. Again, excavating the immediate impact area slows down any further migration of the oil, but you do not excavate to the point where you compromise the building. Then when we installed a mobile treatment unit, we installed inspection wells so we could monitor the movement. This property was right along the shore of Lake Superior, and inspection wells were necessary in order to monitor any migration of oil or microbe amendment. We injected microbes under the home to metabolize the hydrocarbons. Then we installed containment booms along the lake shore to stop any further migration of the oil into the lake. After that, we biopiled the contaminated ice and the snow. We remediated this with a biological agent, the hydrocarbon digesting microbes. We flushed the beach sand using the biological amendment, the BIM 200, and using the mobile treatment unit. Then injected microbes around and under the large trees in the area to ensure their survival. One of the issues on this property, the homeowner had very large mature trees that they did not want to lose. And any further excavation could have compromised the trees, and some oxidants possibly could damage trees as well. Instead, we injected microbes around and under the trees just in case oil had reached there and in order to save the trees. Now, also with the mobile treatment unit, we used it in two different ways. Number one, to establish hydraulic containment, so the groundwater flow from the contaminated area did not continue to migrate into the lake. Second of all, we took the contaminated snow, melted it, and put it through the mobile treatment unit. The results was successful remediation in 6 months, and the actual amount invoiced was $550,000. This was a very sensitive project in that just down the lake, the water intake for Sault Ste. Marie was there. We had the City of Sault Ste. Marie, the Ministry of the Environment of Ontario out on this site, and everybody was very pleased with the process that we proposed, and they were very happy with the results. Here's a photo along the side of the home. You can see in the right-hand side of the building where that dirty spot is, that soiled spot on the side of the building is where the oil tank had sat. You can also see how shallow the groundwater table is and how important it was to establish hydraulic containment very quickly. This is a shot of the recovery well where we established the hydraulic containment. You can see a number of pads sopping up excess oil. You can see how gravelly this area is, so the hydraulic conductivity in this area was exceptionally high. Here's an application of using the BIM 200 and microbes underneath the deck. As mentioned earlier, with the hydraulic conductivity, this surfactant in the BIM 200 lifts the oil as well as containing the microbes and enzymes which digest it and break it down. It's ideal in this situation. Again, it kills all of the aromatic compounds of oil, gasoline, home heating fuel, so the residents can stay in the building during the remediation process. This photo shows where an old abandoned O-pipe discharged into the lake. The sand was treated with the BIM 200 and booms were installed in order to arrest any further migration of oil into the lake. The oil had migrated out into the lake underneath the ice. Portions of it were excavated using a small digger and piled in one central location. That snow was then treated with the BIM 200 biological agent, then melted and sent through the mobile treatment unit in order to further remediate it. The photo on the left-hand side gives you an idea of Lake Superior in the wintertime, the biopiling of the snow awaiting remediation, and the photo on the right-hand side, although it's a little bit difficult to see, you can see the sheen of the oil sitting on top of the water. Here we are in the late fall of the next year. After everything had been put back, you can see the property has been restored to its previous condition. The mature trees had been saved. Thank you for attending Introduction to Remediation Techniques and Technologies. Stay tuned for future seminars on remediation. My name is Chad Trivett. Enjoy your day.